particularly much depth. Like next class will be the first actual technical lecture where we start giving definitions and proving things. Today is just an overview. All right. So basic parameters. Okay, so I'm Aaron. There's a course website. Haven't found it. Maybe the best way to get to it is first to try to find my website. You can find my website by typing my name, Aaron Ross, into Google, and then scroll down on my website. There'll be list of things. And this is what I'm teaching this semester, and there will be a link that goes here, and that's where things like lecture notes and eventually project ideas, anything you need to know for the class, it'll be found on that website. Other thing that is on the website is a sign-up link for the course slides. So the way I'm not gonna use Blackboard or Canvas or anything. We just have a Slack. Everyone, please sign up for it. If there's any announcements, it'll go to the Slack. So what are we all doing here? All class. It's to bring all of us, including me, up to and hopefully beyond the research frontier for what is, I think, a new and important but very much underdeveloped area. So the goal is that at the end of this class, all of you guys will be sort of at or beyond contributing to the research frontier for the mathematical foundations of AI alignment, whatever that is. You guys have an opportunity to help define what that is. And so what does that mean? Well, there's not really a canonical set of knowledge. I'm kind of going to be making this up as I go along, and I'll invite you guys to contribute. But as a result, we're not going to have problem sets or exams in this class. Attendance is going to be important. Please come to the class, whenever you can. That's kind of the point. I hope these lectures are going to be interactive. We're all learning together. And there'll be an attendance component to the evaluation, but the bulk of it will be based on a semester-long project, which I hope many of you will sort of be ambitious about. So it should be a semester-long, ambitious research project. The goal should be to discover something new and interesting and exciting to help contribute to this new field. So you might wonder. But that's actually great. If you're interested in getting involved in research, having a field that seems new and compelling and relevant and important, but underdeveloped is exactly where you want to be. So all of us, you and me, are in the exciting position of being able to help develop and define these foundations. I have some topics in mind. The format of the course will mostly be lectures, so I'll stand here and tell you about some stuff. But this is by no means exhaustive. And so, all of us, I'm learning about this field at the same time as you are. It's very likely that you have some different and better ideas about what we should be learning about than I do. If you do, there's two kinds of ways this could go. Maybe there's an important topic that I have somehow just overlooked that already has foundations. Maybe there's a paper with some mathematical content out there that doesn't seem to be covered in any of the topics that we talk about today or on the website. If that's the case, and you're passionate about it, you should be. I invite you to just claim a lecture. Claim one of the, my default will be to fill the class periods with lectures, but you should absolutely claim one and pick a topic and tell us about it. And it can either be a formal lecture of the sort that I plan to deliver, but it doesn't have to be, right? if it's a paper that you think is interesting, but you don't feel prepared to sort of stand up here and lecture about it, if you want to claim a lecture, you can also essentially structure it as like a group discussion that you should lead. So in that case, if there's a paper you want to talk about, you can assign it that everyone should sort of read it before the class, and you can come up and lead a discussion about it. Okay, so there's an opportunity but not an obligation to do this. If you do want to do this, by letting me know. You can do this in the Slack, or you can just email me. Yeah, so this is not like an obligation. Like, you don't have to do this, but I strongly encourage you to. I'd love to hear. Now, there's all sorts of important topics that I'm not going to talk about, not because I've overlooked them, but because, like, the foundations of those topics just don't exist yet. They haven't been developed, right? And AI alignment, this is a course on like the mathematical foundations of AI alignment. But AI alignment is primarily an empirical field. So there's tons of stuff out there that we're just not going to talk about because it doesn't have foundations. That is an opportunity for a project topic, right? Like if there's an important topic that doesn't have foundations, and there are many such, develop it. Like seize the day. This is your project topic. You can publish a paper about it, okay. So like no problem sets, no exams. How are we going to do grading? So 20%, just to everyone should point. Like 20% of the grade will just be sort of like participation. Come to class and engage actively. You're done. Oh, and of course, if you take a lecture, bonus points. That's great. That's great participation. You don't have to take a lecture, but that's a way to really nail this 20%. And then the rest of the class is just going to be this project, and there's just going to be sort of like a couple of checkpoints. So this is somewhat unstructured. So I encourage you to start thinking about what you want to do early, because I do want this to be an ambitious project, and if you kind of wait till the last minute, it's going to be hard to do it well. So, so this is the class where I'm kind of going to just treat everyone here, like an adult. I'm not going to check in on you all the time, but as a result, you should probably manage your time and start thinking about this early. So what there will be is, at some point mid-semester, there'll be like a project proposal where you just sort of, early in the class as we're going through some stuff, you should be batting around ideas for what you want to do. Like by mid-semester, maybe a little bit before the real midpoint, you should have an idea that's at least a little bit fleshed out, and I'll ask you to turn in a proposal like 1 to 2 pages. That'll be 15% of the grade, and really just to make sure that everyone's kind of on track and thinking about things. Another 15% will be, at the end of the semester, I'll have you guys present the project to the class. We'll just devote the last few weeks of class to presentations. This is another good incentive to, get started early and do something interesting. If you have a terrible project, it's just going to be really embarrassing for you when you have to present it to everybody. And then the bulk of the grade will be the actual write-up. Just turn in something in the style of a research paper, because you hope that many of you research papers that get published, describing, what you did and why it's interesting. So the goal here really is to discover something new and important. So in my experience, research is more fun as a team activity. So I very much encourage you to work in groups. I think a group of 3 or 4 people is kind of the sweet spot for, an ambitious research project that doesn't get completely out of hand. This isn't a hard limit. Have a 5th person in your group, that's fine. If there's only 2 people and you're excited. I do kind of encourage you not to try to do this alone, just because it's, doing research, first of all, it's more fun with other people, and also, that's a good way to really stay motivated to actually do it. You don't right? So aim for 3 or 4, not a hard limit, but think about research as a team. Be ambitious, and as part of that, it is fine/good to use AI tools. Like using things like Cloud Code and Codex can really accelerate research in all sorts of good ways. But like, give me something good. Like, don't turn in slop. I use these tools all the time. It's very obvious if you in the last week say Codex, write me like a class project on this topic. So use the tools to make your research better, not to give me slop. Exposition and clarity are very important. Like if you want your work to be influential, both with me when grading and also with the wider world when you share it, you need to not just like do something interesting. You need to convince people that it's interesting. You need to tell them why it's interesting. Pay attention. So this is sort of all I want to say about sort of the mechanics of the class before I go into like an overview of what are some of the topics we're going to cover. So maybe this is like a good point to take a pause and just poll the room to see if there's any questions about course mechanics or anything like that. Yeah.
Can we do lectures?
Oh yeah. Groups are great. So the question was this thing that I proposed where you can like claim a lecture and either lead a discussion or tell us about something. You can absolutely do that in groups as well. Like as just a general like guiding like philosophy for this thing. I'm not trying to like evaluate you on like the work you have done. Like that's not the point of the way it might be in like an undergraduate class. Like I'm trying to cause us all to learn and discover as much as possible. That's the point of the research projects. That's the point of the lectures. So yes, like if you want to teach us something with a group of people, like do that as well. Again, it probably doesn't make sense to have like a group of 10 people try to like present something to the class, but if you want to give a lecture with a partner, great. Good question. Other questions? Yeah.
Just to follow up on that, timing and pacing, should that take a big part of that?
Yeah. I mean, you have something that you think is only like half the class, fine. But I think a good, like take up the whole class. There's a lot to learn. It's hard to teach something in a small amount of time. Good. Other things. Okay. So, let me give you some rough guidelines for sort of how I'm thinking of sort of organizing the material over the course of the semester. Again, since you guys all will hopefully be doing your own lectures scattered throughout, we're going to like deviate from this, but here's starting. So basically, like I'm going to try to divide things thematically into like 3 sets of questions about preferences, about integrations, about mechanisms. So we'll start off with thinking about sort of just foundations of preferences, like AI alignment. Like, what are we supposed to like align to? Like human preferences. What are preferences? How do we elicit them? And so the first part of the class will be sort of just basic foundations. This will go back to sort of economic foundations of social choice for what are preferences, when can we assume that preferences are represented by like the utility function, what can we learn from elicited comparisons, how can we try to combine preferences in some coherent way from many people who might have different preferences. The second bit will be, okay, like suppose I can learn what your preferences are. Now I know what your preferences are. I know what your utility function is. Then what? Like, what should I even be aspiring to do? And so we'll think about questions like, okay, well, like, suppose I'm trying to make predictions that are useful for you. Or maybe not just useful for you, but useful for many different users who might be using the same, AI system who are interested in different things. How can I, with knowledge of their preferences, or maybe without, make predictions that are useful for the decision problems downstream that a diverse set of users might be interested in. And finally, like, I want to think about sort of the design of mechanisms or institutions. Like maybe alignment is hard. Maybe we can't easily elicit people's preferences. Maybe we can elicit them, but we can't like embed them into models. And the question is, in that case, like, are we all screwed? Like, there are these stories of sort of, like maniacal, like utility maximizers that have the slightly wrong utility function, and like they tile the universe in paper clips, and we're all dead. Maybe it's going to happen, but like, can we think about how to, when I say mechanisms, I kind of mean in the sense of like mechanism design from economics and game theory. Like, can we think about how to set up the interaction between models or institutions in ways that systematically causes outcomes to occur that are safe or that advance the interests of users, even if we can't make that promise from any sort of single component in the system alone. Like maybe it makes sense to think about alignment as something that sort of emerges from interaction or from markets rather than at sort of the individual, the individual component level. That'll be sort of the third. Okay, and so like now I just want to like dive a little bit deeper into each of these things. It's still mostly an overview. Like each of these slides will kind of be like expanded out into like a lecture. But what are the specifics of? By the way, like if you have something in mind that's like not covered here at all, like this is a great opportunity to like volunteer a lecture. So like if I don't mention your topic here, wonderful. So, how do we elicit preferences? So, a very easy kind of preference to elicit is, like, here are two options. Which of these do you prefer? And if you've used, essentially any of the commercial AI systems, ChatGPT, Gemini, Claude, you've probably at some point encountered something like this. You write a prompt, and rather than giving you a response, it gives you two responses, and asks you which of these two do you prefer. Okay, like this isn't the only kind of question you could ask of someone. Like I could say, how much do you prefer? Response A over response B, and ask for like a number. But this is like the easiest kind. It's not clear how someone should fill out. I prefer this response. 2.3 times as much as the other one, and so. That's not generally what people gather. People just gather these kinds of binary comparisons. What do you like better, A or B? Okay. But what you can learn about someone's preferences from pairwise comparisons like this is somewhat limited, right? Like, if I say I prefer A to B, you can't tell from that whether I'm basically indifferent, like A and B are like both like pretty good, but like on the margin I prefer A, or whether like A is like the only one that is acceptable and B is complete garbage, right? Like okay, here are two kind of like bad responses, but like if the one on the right was just entirely like racial slurs or something, like I'd have like a very strong preference for the other one. I might still prefer the one on the left here, but it's only mild, and that's just something that you don't have, like. That's just something that's not identified if you're only collecting binary preferences. So binary preferences are, in some sense, easy to elicit, but they're just not expressive enough to, even in principle, elicit like full details about people's preferences. And so we should think about like what we can learn about preferences just from binary comparisons. The other thing we should think about is, like. ChatGPT asks this kind of question of all of its users. Its users are different people and they have different preferences. Not everyone will agree about which of these two things is the best. And so, to the extent that we're going to go through the exercise of trying to like aggregate these preferences across many users, who have different preferences into like a single behavior for the model. Like we need to think about like what are we even trying to do when doing that aggregation, and what are the limits of what we can do when trying to aggregate fundamentally different preferences into a system that will essentially instantiate like one set of preferences. And so that's lectures. Right, so like a bird's eye view, like sort of the common alignment pipeline for what's called RLHF, reinforcement learning for human feedback, is that initially we'll sort of, for some prompts and completions, gather human preferences. Maybe we'll sort of pay labelers, or we'll just poll our users in production. And it's this kind of like binary preference data. Like, what do you like better, like completion A or completion B? Okay, so we'll collect a bunch of preferences of this binary comparison sort. Then we will train a reward model. And ultimately, we sort of want to do to modify the weights of the language model to produce better, more preferred completions compared to less preferred ones. We don't want at every iteration of that to have to go and bug our human labelers, and so it's useful to try to build first a reward model that can take as input, like a prompt and a pair of completions or one completion, and tell us how good that is, so that we can try to optimize the language model downstream to produce like high quality completions. Okay, so like as an intermediate step, we produce this reward model from the preferences, which takes like a prompt and a completion and tries to just like put a number, like how good is that? And of course, given a set of completions, that induces some total ordering over them. We can order them by how the reward model like assesses them. Okay, so at this intermediate step, we're trying to aggregate preferences from like people who might have different preferences into some model which is inducing some single set of preferences, some single total ordering over these completions, and then we're going to use that to train the logic. And so, like this will take us back to the very early days of social choice, where people like Arrow studied, okay, like what are the fundamental limits for this exercise? You have people whose preferences are represented by a transitive ordering over alternatives. It's exactly the thing we're getting when we get sort of these pairwise comparisons. But you have n different people who have different orderings. And what you're trying to do is you're trying to aggregate them into one single ordering. That's what the reward model is doing. It's taking the different preferences of all the people and it's trying to like aggregate them into a single order. And already in the 1950s, Arrow asked, okay, like what are the limits of what you could do? Like, what do you even want? Like, what are your goals even when you're trying to come up with an aggregate preference ordering given the preference ordering of a bunch of different people? And okay, like it's not clear, but you can start modestly and you can start asking yourself, okay, like what are some like maybe like there's different notions of what is a good aggregate ranking. But like why don't I start by just asking for some really simple things that you'd think you want out of like any aggregate scheme. So here's one, which is called Pareto efficiency, but is like super simple. It just says, look, if every single person out there prefers completion A to completion B, then you could probably learn a reward model that like ranks completion A over completion B, right? Like this isn't even like this isn't constraining you at all if there's any disagreement, right? Like this axiom doesn't specify at all what your aggregation needs to do if there's any disagreement at all. All it's saying is if there happens to be unanimity, if everyone prefers A over B, then the reward model you learn should also prefer A over B. Okay, so that, okay, this seems sensible. Okay, here's another one that seems sensible. It's called independence of irrelevant alternatives. So it says, all right, Suppose I've got a population of labelers. Okay, I'm going to focus on how they rank A and B in proportion relative to one another. So maybe some people like A better than B, other people like B better than A. It's not just like two completions out there. There's this other completion C. Okay, suppose I now modify people's preferences by changing only like how people, how much people like completion C, without changing how they like A and B relative to one another. Okay, so I have like two sets of preferences: my initial set over here, and my sort of modified set over here. And in both of these sets of preferences, every individual agrees on the relative ordering of A and B. You know, if Susie prefers A to B on the left, she also prefers A to B on the right. Right? If Bob prefers B to A on the left, he also prefers B to A on the right. The only thing different between the left and the right is the relative preferences they have for this like different ordering C. Okay? The independence of irrelevant alternatives says that the social aggregation function should, however it ranks A and B, it should do it the same way on the left and the right. Because nobody's preferences with respect to A and B have changed on the left or the right. Okay? So that's like independence of irrelevant alternatives. There's some like anecdote about Sidney Morgenbesser, who's a political philosopher, going to like a diner and the waitress says, would you like the apple pie or the cherry pie? Then she comes back and says, I forgot to mention we have a special today. We also have blueberry pie. He says, in that case, let me change my order. I'll get the cherry pie. A weird interaction because normally people respect the independence of the relevant alternatives. Okay, does this make sense? Yes.
In the example you showed, what exactly are the objects we're trying to order?
So here, it's like the completions. So like given a prompt, like there's various responses that the language model might give you. Those are like the alternatives that you have preferences for. Make sense?
But like once we have the preferences of individuals, I mean, it's slightly confusing to me because even when I ask the same question, I get a different answer sometimes. So it's like,
yeah. So there's all sorts of answers you could get when you ask the question, and these things are stochastic, so you might get different. But in principle, like fixing the question, you sat down and thought about it. You might have preferences over all of the different answers you could get. Right? It might be like take a long time to like read over them and figure out which ones are right. But like you could sit down and in principle like order from best to worst your preferences over answers. So that's kind of like the object we're thinking about being ordered here. Does that make sense? Okay, and so what does Arrow say? Well, it says, like, look, if you're trying to come up with a rule to aggregate different people's preferences, and you want that rule to satisfy both of these axioms, Pareto efficiency and independence of irrelevant alternatives, then there's only one way to do it, and it's to have a dictatorship. It's to say, look, the aggregate rule is just going to be like Alice's rule. It's just going to be Bob's rule. Like we're going to like ignore everyone's preferences except for one like person that we identify ahead of time, and we're just going to like use their preferences. And that's kind of a negative result because that's not really an aggregation at all. It's just using one person's preferences and ignoring everyone else. Right? So this is a very negative result. It says if you're looking for aggregation rules that satisfy these two sensible sounding axioms, Pareto efficiency and independence of irrelevant alternatives, like you're kind of screwed. Like there's no way to do it such that you actually have a meaningful aggregation. The only such aggregation rule that satisfies these two is a dictatorship that just points to someone and sort of regurgitates their preferences. Doesn't even attempt to aggregate it with others. Okay. This is like Arrow's impossibility theorem and should confront us very early on with this kind of like a basic impossibility result for the thing that sort of, maybe RLHF is trying to do in this intermediate stage where it learns a reward model. The reward model is doing this aggregation and, like there are limits to what you can do there. Yeah.
Is there any restriction
Now the world is kind of like finite ultimately. Like there's no dependence on a number here. So, there's no moral restriction in the sense that you could take the number of completions to be to the number of atoms. Fine. But I don't want to confidently say that nothing funny could happen in like a continuous world. So I won't say that. But there's no meaningful moral restriction because there's no dependence on the cardinality of the finite sets, and like the universe is ultimately finite. Good. Other questions? Yeah.
If we have a random dictatorship and suppose the dictator is kind of indifference between choice A and B, while all the others is kind of, they have strict preference between A and B and they are all the same side, like they all prefer A over B. So can we slightly manipulate the joint preference by replacing the dictatorship preference and replacing indifference by a slightly stricter preference?
Okay, I didn't totally understand the question. One part of it is that I can use randomness, right? I can randomize between things, and so if I'm allowed to use randomness, okay, I can have a random dictatorship, meaning I pick out of a hat first who's the dictator, and I'll use their preferences. But what I can't do is I can't choose who the dictator is as a function of the other preferences. So I can't look at the other preferences and try to do some aggregation by cleverly selecting amongst them. So random dictatorships don't sort of get out of sort of the moral conundrum here, which is that you're not doing any aggregation. You kind of have to choose the dictator randomly or not before you look at the preferences.
So I'm thinking about for example, there are 3 people in total in this economy. One of them, so it's we randomly assign the dictatorship to one of them. And this specific one being chosen as dictator at this moment, he has indifference between 2 commodities, let's say. And for example, while all the other 2 people who are not chosen as dictator at this moment, they have strict preference over between one commodity to another one.
So for indifferences, you have to fix a tie-breaking rule, because ultimately you're going to need to output one completion, say. And you can fix any tie-breaking rule, but you have to fix it, again, ahead of time. You can't choose the tie-breaking rule as a function of the other preferences. Yeah, that would be a loophole. Then you could just have someone who is indifferent between everyone, and you say, okay, they're the dictator, but I'm going to break the indifferences always in some arbitrary way. Now, that doesn't get you out of the basic concept. Yeah.
The dictator ahead of time, how does that guarantee the Pareto?
Because if Pareto efficiency just says if everyone prefers A over B, then you have to prefer A over B as well. Well, if everyone prefers A over B, so does the dictator, whoever they are. So a dictatorship is Pareto efficient and satisfies independence of irrelevant alternatives. It's just not doing very much aggregation.
It's if PE, then it must.
Exactly. But Pareto efficiency is a very, very weak requirement, which makes the impossibility result more striking. If there's any disagreement at all between which is better, A or B, Pareto efficiency doesn't put any constraint on the aggregation rule at all. The only time it's binding is if everyone uniformly agrees that A is better than B, in which case so will the dictator.
Oh, I see.
Next lecture, we'll derive this next lecture. But okay, maybe in light of this, we should sort of think of alternatives to the standard, maybe pipeline, where at this intermediate stage you learn the reward model. It is really the reward model that is inducing this total ordering over completions. It's not the LLM itself. The LLM is stochastic. You type in a prompt and it'll give you a distribution over different every time. And so the object that kind of Arrow's impossibility theorem kind of binds to most strongly is not the thing we're trying to build in the end, the LLM, which is giving us a distribution over completions, but rather the reward model. So maybe we can avoid that intermediate step. Okay, so given a prompt, this will induce some distribution over completions. And now let's just like think about how we might evaluate two distributions over completions and think about which of the two is better for some population of users. So say we know that our users come from some distribution. I'll just identify users here with the preference ordering they have. And now I've got like two candidate distributions over completions for some problems, P and Q. And I want to know, like, how should I even think about which of these two is better? Well, here's one way to think about it. Like, here's like a thought experiment. Say, okay, I'm going to sample a random completion A from distribution P. I'm going to sample another distribution B. Sorry, I'm going to sample another completion B for distribution Q. Okay, so these are two things that like ChatGPT could get back to you with when you ask it a question. And then I'll sample a random user from my population. And I'll just ask them, hey, user, do you prefer A to B or no? And if the answer is yes, I will say, okay, like P won this time. And if no, I'll say Q wins. And of course, this is a stochastic comparison. I'm sampling completions, I'm sampling users. And so for any two like distributions, P and Q, there will be like a probability that P wins and another probability that Q wins. Let's just say that P defeats Q in this tournament if it's more likely to win. Maybe they're tied, but it's just going to be like a probability that P wins, and there's a probability that like Q wins if we like conduct this thought experiment. And so, having set this up, this thought experiment, you might ask, well, can I find a distribution over completions that defeats everything, or at least ties them? Like if I have two distributions that are identical, sort of competing against each other, of course each one will win about half the time just by symmetry. But can I find like a single distribution over completions that defeats or ties all challengers? Maybe that's what I want to use, right? Because if I have something that is defeated, maybe I should use the thing that defeats me instead. So can I find a distribution that defeats all challengers? It's not obvious that I can, by the way. Like this is kind of the thing that plagues aggregation rules, and that sort of Arrow's theorem is related to. That you could have just cycles, right? I could find that P defeats Q and Q defeats R and R defeats P, and maybe there is no like universally best one, right? So this is like it's not obvious what the answer is to this question the first time you think about it. Like, is there a distribution over completions that defeats all challengers? But it turns out the answer is yes. In sort of the older sample choice literature, this is what's called a maximal lottery, and it was kind of like rediscovered in the AI alignment literature, called it a von Neumann winner, and then people realized these were kind of the same thing. And so, like, this is a different way you can think about aggregating preferences, taking advantage of the fact that, like, by their nature, like LLMs are stochastic objects. We can associate with a prompt like a distribution over completions. We don't have to fix a fixed completion. And trying to do this as our objective, this like avoids the whole like preference model step, which is the thing that was like artificially inducing like a fixed ranking over completions. And so so you could set this as the goal, like try to find a distribution over completions that defeats all challengers. And this is the goal of sort of some subliterature that sort of is called Nash learning from human feedback. Nash learning because, as we'll see when we study these things, what P star is kind of like the mini-max equilibrium or the Nash equilibrium in like a particular zero-sum game that you construct, in which sort of your strategy space and your challenger's strategy space are just distributions over completion. So sort of you want to find the Nash equilibrium of some particular zero-sum game to like solve for this object. That's why sort of the particular training procedure is called Nash learning.
I guess I was just wondering, this isn't actually a guarantee that some other challenger cannot defeat this P star distribution, right?
It is. P star defeat, but like, at best you can tie it. There's no other challenger that can defeat it.
Okay, because I guess
Because like the probability, if I'm fighting two distributions against each other, P versus Q,
Right.
either P wins or Q wins. Right,
Sure.
in particular. So like the probability that P wins is 1 minus the probability that Q wins.
Sure,
And,
but
and so like I can't have that P defeats Q and also vice versa.
right, but you could have like P defeats Q, Q defeats R, and then R defeats P.
Right, but the R defeats P can't happen if P defeats all other challengers. So there
Right.
can be cycles like this.
I see, but
But
you
they can't involve a maximal lottery because a maximal lottery is definitionally something that is not defeated by anything else.
I see.
And you're right, there can be cycles. That's exactly why it's not obvious a priori that a maximal lottery even exists. But it does.
I see.
Does that make sense? Okay, good, yes.
Do we fix like prompt for this?
Do we-
Do we fix like prompt?
That's right. Yeah. So in all of this discussion of preferences, kind of like imagining that we're fixing a prompt and these preferences are over the. Of course, in real learning, like we don't gather preferences for all of the infinitely many prompts in the world. We try to sort of learn a parametric model that captures this. But in all of these discussions right now, and really, like probably in this class, as you talk about it, I'm not going to talk about sort of the process of trying to learn a fit a parametric model. I'm just imagining that we're able to do this. Yes.
Say if P star, we're just trying to find a distribution. Well, P star can't really overlap with any other distribution.
You mean you start can't overlap?
If you think of P star as it defeats all other distribution, then most other distribution can do is touching.
Oh no. So it's not like it has to have a disjoint support from others. Like defeats doesn't mean like it wins the thought experiment with probability 1. It just means it's more likely to win than to lose.
Oh, okay.
Right, so it totally makes sense to have you can tie, right? So it makes sense to have P fight against another copy of P, in which case it'll tie. So it's not that it always wins. Defeat means it's more likely to win this comparison. Good. Other questions? Yeah, and so because these things are like, because maximal lotteries turn out to be like the equilibrium of zero-sum games, which are objects that are easy to compute, we'll see how to compute this stuff using no-regret learning, and I'll probably spend a class just teaching about no-regret learning, because that's so. Okay. Good. So like so far, we've just talked about preferences as like ordering. It's like I prefer A to B or not. But like that doesn't get at the strength of my preference. Right? Like maybe I'm kind of on the fence between A or B, or maybe like A is like way better than B. And oftentimes it is convenient to model people and agents as having utility functions, which capture not just ordering but sort of strength of preference. Okay, so like for example, there's a set of actions I can take, and there's maybe a set of states of the world that are decision relevant for my actions. Like maybe I would model an agent for myself as having as assigning like a number to some combination of action and state of the world, saying, okay, like this is how much utility that I get. This is how much utility I get if I take action A in the state of the world, and maybe if there's randomness either inherent in the world or because of my own uncertainty, I would try to choose actions that like maximize my utility and expectation. Okay. All right. Like, when is that a reasonable modeling assumption? Oh, and like we might set out as goals when we're trying to figure out like what is desirable, what should we like be working towards. So maybe like maximize social welfare. Maybe I want to arrange things so that when I sum or average everybody's utility, that's as big as possible. Okay, so a basic question is, in doing this, when is it a reasonable modeling assumption, either for people or for AI agents, that their goals can be expressed as utility functions? In principle, like say I can ask you like, what do you like better, A or B? looks like pretty easy to ask you about for like a fixed completion. Pair of completions. Do you like completion A or completion B? In principle, like it might be hard to like get you to like spend the time to like answer the question, but like I could ask you about distributions or lotteries as well. Like I say, look, here's one distribution over completions. Here's another distribution over completions. You're gonna have to sample from them a bit, so like learn about them. But like, please do that. I could ask you, do you prefer like distribution P or distribution Q? Like I could ask you about just pairwise preferences for lotteries as well. And it turns out that if your preferences over lotteries satisfy 4 axioms that are called the von Neumann-Morgenstern axioms, they're all kind of reasonable. Like completeness is just that you have a preference. So if I for any 2 lotteries, you have a preference. Transitivity just means, okay, if you claim to prefer P over Q and you claim to prefer Q over R, then you should also claim to prefer P over R. Continuity is about your preferences shouldn't like change discontinuously as I like add randomness. So like if you prefer P over Q over R, then there should be some extent to which I can randomize between P and R so that you're indifferent between that and Q. It shouldn't be that you sort of discontinuously go from like preferring the lottery over Q to not. So, like there should be some point of indifference. And independence, another sort of like similar to independence of irrelevant alternatives. It says if you prefer P to Q, then for any alternative R, you should prefer a lottery that mixes some fraction of P with R to a lottery that mixes some fraction of Q with R. So all reasonable assumptions, and like if your agent satisfies these assumptions, then I can always represent their preferences as a utility function. In fact, this is if I can represent your preferences as a utility function, you have sort of obviously satisfied these axioms. So like these are sort of necessary and sufficient conditions for it to be sensible to represent human or agent utilities, human or agent goals as utility functions. And it turns out, right? So this sort of justifies. This is mapping out when we're justified in modeling goals as utility functions. It turns out that if we're going to try to like aggregate preferences by also with like a utility function, like if the sort of social preferences also satisfy these axioms, then if we want the social preferences to satisfy the Pareto property, the same one from the arrow axioms, that if everyone universally prefers P to Q, then so should the aggregate, then the only social goal that can accomplish that is to maximize either social welfare or some weighted social welfare. We can weight different people differently, but like maximizing weighted sums of utilities is kind of like the only thing we can do in that case, which justifies in general that as being so, maybe back to the, RLHF or NLHF pipeline. Suppose all we can do is we can list comparisons. So, as we noted at the beginning, this doesn't let us elicit the strength of preferences, like you might pick. It's in front of you. This doesn't let you elicit the strength of preferences, right? I can tell maybe that everyone prefers A to B, but I can't tell by how much. Kind of the sort of preference elicitation that is done. But maybe my goal is to find an LM that's going to maximize social welfare. I want to maximize the sum of everyone's utilities because this is the only thing that's going to satisfy the Pareto property. So, there's kind of like a conundrum here because the kind of data that I'm gathering isn't even sufficient to like identify the objects that I need to in my objective. Like I want to maximize people's utility, but like even in principle, I can't figure out what your utility function is if I can only ask for sort of pairwise preferences for single completions and not for lotteries. Then we can ask, well, okay, like, you know, there's this uncertainty about what people's utility functions are. I know something about them through the preferences, but I don't know exactly what they are. I can say, okay, well, so for any like mapping I might have from these preferences to, you know, some distribution over completions, I might worry that there's some distortion. I haven't maximized social welfare. I've done worse by some factor. And so that distortion factor will be the worst case over any set of utility functions that are consistent with the pairwise preferences that I've elicited. Right, so the worst case over what could be, given the data I've gathered, of the ratio of the welfare induced by the optimal lottery for those utility functions. If I could optimize social welfare, if only I knew what they were, with the welfare of the lottery that I found, not knowing what the utility functions were. So let's call that the distortion factor. And in the face of this uncertainty about what people's utility functions are, I could ask for trying to come up with the lottery that minimizes this distortion factor, that gets sort of this worst case degradation from pointwise optimality to be as low as possible. And it turns out that, you know, you're not going to be able to do this with sort of an intermediate reward function, like in the sort of standard RLHF setting. But a maximal lottery will do just this. So it's this goal of Nash learning from human feedback, of finding directly a distribution over preferences that kind of defeats every other one, will be the object that sort of optimizes for this worst case distortion. And this sort of solving, in some way, this problem that our goal of maximizing social welfare is defined in terms of these objects, utility functions, that are just not identified from the kind of pairwise comparison data that we gather. Okay, makes sense? Second part of the course, information. So, I suppose I've learned people's utility functions. Obstacles there, but suppose I've done it. And so, you know, maybe like the reason the user is interacting with the LLM is because they've got some decision they need to make in the world. They need to, you know, decide what college to go to, or what drug to give their patient, or, you know, like what project, of course. And, you know, there's different actions they can take. What's the right action for them depends on what the state of the world is. They don't know what that is. They're trying to learn more about it by talking to the LLM. And so they've got some utility function that depends both on the action that they could take and the state of the world, and tells them how happy they are with the outcome. So, you know, like if they knew what the state of the world was, then maybe their problem would be easy. So if they knew either exactly what the state of the world was, or they knew a distribution from which it was drawn, they could best respond. They could choose the action that would maximize their utility and expectation. Problem is, the reason they're interacting with the AI system in the first place is they don't know what the state of the world is, or maybe even a distribution for it. You can ask, all right, well, you know, like, we're trying to design this AI system that's useful not just for one person, but for many people. Different users might have different utility functions. How can I design a system, like a statistical model, that can make predictions that are useful for all downstream decision makers, no matter what their utility functions are? Now, if we knew the world perfectly, if we knew the distribution of y given all of the context that we have, then we could just predict that. Like, the distribution on y is a sufficient statistic for the best response problem, like no matter what your utility function is. But in general, it's difficult or impossible to learn, you know, like true conditional distributions, conditional on everything we know. And so we don't want to just say, okay, well, we're going to solve this problem through perfect learning. We want some. Now, okay, so here's just like a picture of sort of the kind of thing we want to happen. We want to have some statistical model that, given some context, prompt, can predict something. Maybe it's not the true distribution on states of the world given context, but something that can be used as if it is. And we want, without knowing who our user is, we might have many different downstream users who care about different things. They've got different utility functions. We'd like this thing that we predict to be sort of useful for all of them in deciding what to do. Different ones of them might take different actions given the same prediction because they care about different things. Now, it's hard to sort of predict the true probability of y given x, but there's a substantially weaker statistical condition called calibration, which is easy to satisfy. It just asks that our prediction be unbiased, conditional on the value of the prediction itself. So if we predict that chance of rain tomorrow, calibration asks that on the days that we predict that, conditional on that prediction, it should actually rain 20% of the time. So it's just a simple, self-consistency thing. The predictor should just be statistically unbiased, conditional on the prediction itself. And, we're going to make these predictions. What's a user going to do? Well, they ultimately need to, choose actions. So they're going to come up with some policy that is going to take as input our prediction, and it's going to decide what to do. A mapping from predictions to actions. Nice fact about calibration is that even though it's much weaker than perfect learning, predicting the true distribution on y given x, it is actually both necessary and sufficient. It exactly characterizes the following property. Okay, calibration is necessary and sufficient, such that for all downstream decision makers, no matter what their utility functions are, if they're thinking about amongst all of the policies they could possibly use, mapping forecasts to actions, what is the best one? They will all come to the conclusion that the best one is to just best respond to the forecast. That is, the best thing to do amongst all policies you could possibly use is to treat the forecast as if it was the true conditional probability, even though it's not necessarily. Okay, so calibration provides this very nice interface between prediction and decision making that is agnostic to what the downstream utility function is. This condition doesn't mention the downstream utility function at all, such that you can plug these predictions in to any downstream utility function and get this guarantee that the best policy to apply is this very simple best response policy. Like a nice reason on calibration in systems that are going to be sort of ultimately part of some decision-making pipeline where you don't necessarily know what the goals are further down the pipeline. Maybe because there are many such goals, because the same prediction component is going to be used in many different decision-making pipelines. And, it turns out that in part because calibration is a simple distribution, it is possible, even easy, to produce calibrated forecasts in settings that would seem very difficult. We don't need to have a really well-behaved learning setting where there's a fixed distribution and we, have samples from this distribution and we assume that at test time we face exactly the same distribution we trained on. No, you can have a fully adversarial setting where the distribution is shifting arbitrarily and unexpectedly over time, or maybe there is no distribution, the sequence of predictions you need to make are about sort of adversarial events. Using ideas closely related to no-regret learning and Blackwell approachability, which you'll learn about, it's fun, you can guarantee that you make a sequence of forecasts that, of course, might not be correct in any, Platonic sense. In an adversarial setting, correctness doesn't even, really parse, there is no underlying distribution, but that are calibrated, and therefore plug into decision-making pipelines in very nice ways. Okay, and there's a variant of calibration called decision calibration that kind of gives you efficient generalizations of this even to pretty high dimensional settings. So we don't have to be talking about, like predicting like the probability of rain, like a binary event. We could be talking about complicated events, maybe trying to figure out like what your diagnosis is. Maybe there's 1,000 different diagnostic codes in the hospital. We can still talk about decision calibration in ways that have sort of nice, provide a nice interface between predictions. And these tools will also be useful. Question.
Sorry, regarding the calibration part,
Yeah.
like you mentioned, like the best response, it's kind of the best response if you provided. So I would like to ask about, like, in what sense it's the best response? Because if I remember correctly, if suppose two people are using calibration to trying to calibrate the strategy, it is not the natural equilibrium it is generated. It is the correlated equilibrium that is generated. So in that sense, it is not a best response in a usual sense, right?
It's the best response given the sort of information set. Right? So a correlated equilibrium is still about best response.
Yes, fair.
It's best response in a correlated equilibrium. There's sort of a correlating device,
I see.
and the signal I get from the correlating device gives me some distribution of what everyone else is playing, and the correlated equilibrium condition is that I must be best responding to that distribution.
I see.
Yeah, so yes, but not in conflict with. Good. Other questions?
Go back to the previous slide. So I'm wondering about the third bullet point. So are we thinking about this calibrated fx as like the conditional mean, which is like the sufficient statistics for us to do the downstream decision, or?
Say that again.
So are we thinking about the fx as a sufficient statistics for doing the downstream decision? Because you said that the best response is like conditional on fx, then we can generate the best response which dominates all the others. So is that,
Yes. So like I go into this are that you have the utility function that maps actions across state of the world. So if you knew, so to figure out what your expected utility is, it suffices to know a distribution over the state of the world. That's the object that the prediction is trying to forecast. So like I'm predicting for you a distribution over the state of the world. And the claim is that, of course, if I gave you the right distribution over the state of the world, you would just choose the best response if you wanted to maximize your expectation over that distribution. The claim is, if all you know is my forecast, then that same optimization is optimal for you, even if I don't promise you that I'm predicting the true distribution over the state of the world. It's enough that the distribution be calibrated. Does that make sense? Yeah. And there's like a caveat here, which is that, not promising to dominate, like, best response is the best policy amongst all policies mapping forecast to actions.
oh, I see.
It's not promising it's better than things you could do with information, additional information not contained in the forecast. Maybe you've just trained some much more capable AI than I have, and you have much more information about what's going to happen in the future compared to like my prediction. It's not saying you should ignore your information and just best respond to mine. That like it's optimal only amongst policies mapping my forecast to actions. And there are, maybe we'll talk about them. There are sort of strengthenings of calibration, things like multi-calibration that condition not just on the forecast, but also on externally observable things that kind of strengthen this kind of guarantee. Good. These calibration tools are also useful for collaboration. So, AI models are getting better and better under our feet. But I think that, like, at least in the near-term future, people will continue to have value added in decision pipelines together with AI systems and vice versa. Like, there's not going to be too many high-stakes settings where we want to turn over all decision-making power to like the AI. Like humans should stay in the loop. And similarly, there's probably not too many important decision-making settings where we want to have people not using AI tools, like these tools. And so, we're going to want ways for people and AI tools to collaborate to reach better decisions than either of them could have obtained alone. And like the reason why people still maybe have something to add is, at the moment people might have broader contextual knowledge, sort of qualitative observations that are kind of hard to communicate to the AI, like they can smell stuff. It's hard to like describe smells to the AI. Those smells might be relevant for some decisions. And of course, like, the AI system has all sorts of useful knowledge, but much of it is sort of in an inscrutable form that would be hard to just, like load into my head. And so, like, there's the question, how can we make decisions that successfully integrate the expertise of both parties in a way that improves on either performance alone? And, you might think, okay, well, everything that's decision relevant that's known by either of the parties to one of them, and they will make the decision. But an important premise here is that's kind of hard to do. Like I can't read all this, AI's training data, and I can't express all of my sort of contextual knowledge and implicit observations, in the text box. So this is related to something, again, studied by, an old theorem in economics. It's called Oman's agreement theorem. And Oman's agreement theorem talks about sort of a stylized setting. It says, look, there's two, like, perfect Bayesians. What does it mean that you're a perfect Bayesian? Well, it means that, I have, like, some correct prior belief over the joint distribution of everything I might observe, everything you might observe, and the outcome. So do you. And we have different observations. So you and I might initially have different posterior beliefs. But what we're going to do is we're going to like have a conversation amongst each other. I'm going to tell you my posterior belief about some event. You, being a perfect Bayesian, will integrate over all of the things I might have seen that would cause me to have that belief, and will update your belief. You have a new posterior belief. You tell that to me. I similarly do a perfect Bayesian update. I have a new belief. I tell it to you, and we go back and forth. And Oman's agreement theorem says this doesn't continue forever. We'll eventually converge to the same belief, and in an accuracy improving way. Like, of course, I can't become less accurate as a perfect Bayesian by conditioning on more stuff. So this is a way to come to like accuracy improving agreement, and in some settings, like provably aggregate information through some low bandwidth channel. So we're not talking about our observations. We're only talking about our beliefs. Now, it's kind of hard to like implement like Oman's agreement theorem because all of the objects it speaks about are sort of completely both computationally and epistemically implausible. Like I don't have a prior belief over the joint distributions that I and ChatGPT have about like the patient just like walked into my office. It's not even clear what it would mean to have such a thing, and if I did, like, conditioning on all of the things that I might have observed that would cause me to have some belief, and updating ChatGPT's posterior belief over that integral, like that's would be a sort of implausible computation. So, so Oman's agreement theorem tells like a nice story, but it's not like a computationally or like epistemically like implementable story. But it turns out that you can actually get the same conclusion, in fact, a stronger conclusion. You get fast convergence to sort of accuracy improving agreement in quite general settings. Even without all of this Bayesian machinery, it's going to suffice that in the conversation that we have, in my part of the conversation, at every round, the things that I say are not correct that they would be for a Bayesian, but are just calibrated, conditional on what you said at the previous round. If you satisfy the same condition, call this conversation calibration, we recover Oman's agreement theorem completely. And this gives us, because we have fast tractable, fast algorithms for guaranteeing this kind of calibration, this gives us a very, very sort of communication efficient way to aggregate beliefs in an accuracy improving way. We don't need to talk about the observations we made that caused us to have those beliefs. We only need to talk about the beliefs themselves. finally, mechanisms. Yes.
Sorry. So, if I remember correctly, agree to disagree just need one time of communication. It doesn't need repeated, right?
So Oman's original theorem actually doesn't talk about dynamics at all. It's kind of a
It's just one time.
It's kind of a no. It's not. It's kind of a fixed point theorem. It's about common knowledge. So it says that if I'm a Bayesian, you're a Bayesian, and
we share this.
we have common knowledge of each other's posteriors, then we both have the same posterior. But common knowledge is like the limit of sort of an
Yes.
infinitely long conversation. I know that you know that I know that you know.
Oh yes.
Ad infinitum. And so like this thing that I said where I said Oman's agreement theorem actually implies that this conversation will eventually converge. That's actually not in Oman's original paper. That's a later result. So Oman's original paper is sort of about a fixed point, like the limit of an infinitely long conversation. And later work talked about dynamics. Okay. Mechanisms. Finally. Okay, so maybe alignment is hard. Oh, yes.
Reference theory and expected utility capture some observed regularities in human behavior, yet sometimes, in some cases, they incorrectly predict or describe such behaviors. So is there a way to approach AI alignment without invoking preference theory?
Yeah, great questions. So, like, it is not clear that modeling AI agents or even people as having utility functions and acting to try to maximize them is like such a faithful model. And this has been known in economics for a long time, the whole field of behavioral economics that tries to come up with other heuristics. I'm using that not because I claim it is like unambiguously the right thing, but just because like I don't think there's a good second choice that I know of that isn't subject to even more criticisms. But this is actually like a very good project topic or lecture topic. Like, a lot of what I'm going to be telling you about is going to be leaning on this model of like, rational agents as, having consistent preferences that maximize utility. Is that true? Like, is that true of AI agents? Is that true of people? And if it's not, like, how else can you reason about this? What's a better foundation? So, a good point. I don't know the answer. You should discover it. Good. Other questions? Okay, so mechanisms and institutions. Maybe alignment is hard for some of the reasons we've talked about, or for other reasons. Like maybe it's hard even to like elicit or discover user utilities. Maybe we don't know what to align to, or maybe we can figure out how to elicit them, but actually, it's hard to embed these goals consistently into machines. Maybe we can't train machines that sort of reliably pursue the same goals as we do. Or maybe organizations like OpenAI or Anthropic or XAI do succeed in aligning the models they produce with their goals, but maybe their goals are not the same as our goals. So, like, are we screwed in that case? Or might it be possible to set up mechanisms and structures through which, when these individually misaligned agents or institutions interact with one another, nevertheless, we get to safe or even beneficial outcomes. I want to think about it. So there's this idea of like scalable oversight. Maybe like one of the first ideas in this literature is like AI debate. And so the idea is that a human being or maybe a trusted but weak model is able to be involved and can sort of adjudicate bite-sized local claims for correctness without themselves being able to solve or even really verify the solution to large problems of interest. Like maybe, some AI says it's, discovered what I should do to like end world hunger, and I'm like, all right, prove it to me. They like output, 100,000 page like PDF and like 10 gigabytes of code for other simulations. I'm like, oh shit, what am I supposed to do? I can't come up with it or even really verify it. The idea for AI debate is that maybe we can sort of set up two AI models, kind of in the role of like prosecutor and defense attorney. One of which is trying to like establish the claim, and the other of which is trying to poke holes in the argument. And the idea, again, at a high level, is that we'll assume that the models are sort of arbitrarily powerful. So this is some near future. The AIs are more powerful than they are today, but the adjudicator, which is, you know, like a lowly human being, perhaps, is computationally bound. So what we want is that if the claim is false, then through this interaction, like, prosecutor should be able to like identify some like bite-sized claim that the adjudicator can evaluate that sort of establishes some inconsistency in the argument, like finds a problem with it. If the claim is true, then they shouldn't be able to. And so, so suppose you've got, you know, two models tasked with either establishing or falsifying a claim that are rewarded, you know, for being able to complete and sound and polynomial type judge. And the model is that the AI models can perform arbitrary computations, but you know, the adjudicator has limited time, so we're only going to let them interact for polynomially many times. So, you know, modeling this at, you know, a very stylized level, what is possible to establish is that if both players, the adjudicator, if both the, you know, prosecutor and defense attorney models are playing optimally in this game, then this process is going to be sound and complete. It will allow the adjudicator to reject false claims and to accept true claims for every problem in the complexity class P-space. P-space is sort of a much larger class than NP. You know, problems in P-space in general don't have polynomial time algorithms even to verify the solutions, let alone to come up with them. And that's the added power of the debate framework, that sort of you can get efficient verification by having these much more powerful models interact in this sort of adversarial game. Alignment through competition. So suppose we've got AI models that are, we've succeeded in alignment, but unfortunately what that means is that the AI models are aligned with the goals of their creators, not necessarily with your goals. Okay, so maybe, you know, these models represent the preferences of like Sam Altman and Elon Musk and similar, which, you know, may or may not be the same as your goals. And maybe what they want is influence. Like, you're going to interact with these models to inform your decisions. And maybe, you know, like Sam Altman cares about what you buy. He wants to run ads that'll cause you to, you know, buy more Nike shoes so that he makes money. Or maybe, you know, Elon Musk wants to influence who you vote for. But of course, like, we seem to be living in a world in which there's not just one, like, AI provider monolith. Like, there's a bunch of them, and you have a choice about which one to use. And someone who wants to influence your behavior needs you to use their AI model. Like, if I use Grok, then, like, it's not influencing, like, what I do. And so, if these parties want to influence my behavior, they need, you know, in a world where I have choice over which model to use, you know, they're sort of, you know, they need to, like, engage at least a little bit with my preferences. So, you know, the organizations, they're misaligned with me. They don't have the same utility. But maybe they're also misaligned with each other. Maybe they're differently misaligned with me. Right? Maybe different ones of them want different things. Can we take advantage of that? And so, like, in choosing which models to deploy, trying to influence my behavior, they're engaged in a strategic game with one another. And is there a condition that is maybe weaker than perfect alignment? That there's someone who just has my goals in mind that is sufficient to promise that in all of the equilibria of this game, I actually end up as well off as I would have been had there been perfect alignment? The answer is yes. You can sort of give a substantially weaker condition that we call market alignment, which is essentially that my utility function doesn't have to be equal to any of these providers' utility functions. It just needs to lie in the convex hull. It's not, not guaranteed to be true, but is substantially weaker than full alignment. Finally, last thing I know that I want to teach you about at this point is delegated approval. So, we've got these agents that can do increasingly interesting things over long time horizons, right? You can fire up Codex and you can give it a task that's going to take 10 hours, and you can press go and maybe come back and see what's done. But you don't trust it that it's going to correctly advance your goals everywhere. You're worried it might delete your hard drive or something. You might not want to let it do arbitrary things without getting your approval. Right? So you could conservatively require human approval at any step that requires taking an action that's hard to reverse. That removes a lot of the benefits of interaction. It's very annoying if I set Codex on some long-running task and I go into the office and I come back and I find that 1 minute into the task it was hey, can I check out this website? And it's just been waiting for me the whole time. So it removes a lot of the benefits of automation if I make it ask me for permission for everything. Now, Codex has this great feature. Have it ask me for approval for everything. I wouldn't want to do that. Then I could never walk away. I could give it full access to my computer and let it do anything without ever asking anyone for permission. That looks kind of scary, it's written all in red. And so, there's this thing that I, and probably all of you, choose, which is this middle option that's called Approve For Me. And it's great. It just, does stuff, and it never asks me for permission. But what it's doing is it's firing up another GPT agent, and whenever it wants to ask someone for permission, it doesn't ask me, it asks this other agent. That agent approves it, so things are great. But the question is, when is a setup like this actually giving me any extra protection? Is there some circular thing? I have the main driving agent behind this approval barrier because I don't trust it to correctly advance my interests. Why should I trust other agent, which is probably kind of a similar agent to correctly advance my interests? Do I need to have another approval agent one layer down? Is this turtles all the way down? Or generally, you can sort of set up a model that looks kind of like this. You've got some stateful MDP. You've got your driver agent, your main GPT agent. I'll call it the proposer. And whenever it wants to take an action, it'll ask for approval, not from you, but maybe to a panel of agents that you've delegated to give approval. And you, in designing this mechanism, get to figure out what the authorization rule is. Maybe I'll let them do it if they all unanimously agree it's a good idea, or maybe if one of them, if it's almost unanimous, I'll let them do it, or here's where the design ability is. And if this rule approves, I'll execute whatever they did. Otherwise, I'll use some baseline policy, maybe ask a human being. And then whatever action is taken, which actually changes the state of the world. And this is just a closed. Are there conditions weaker than full alignment that will promise me safety relative to the baseline policy? That no matter what the proposer agent tries to do, I'll always have expected utility for running this control loop that's better than the baseline policy. And it turns out that you can exactly characterize this. You give an if and only if condition. And the answer is very similar to this sort of market alignment idea. It sort of suffices that these sort of reviewer agents have utility functions that contain my utility function just in their non-negative span. Guaranteed to hold, but it's much weaker than individual. So again, wrapping up, this is just some random collection of topics satisfy the intersection of like some formal work has been done on them, and I sort of came across them over this summer while I was thinking about these things. There's tons of important work that this list doesn't cover. Surely lots of work that actually has established very formal foundations that isn't on my list. If you discover something that seems worth talking about, this is exactly when you should claim a lecture or lead a discussion and stuff. And AI alignment is like primarily an empirical field. So there's tons of important topics on which lots of work has been done. Just none of it is sort of foundational. None of it is developing sort of mathematics to understand it. Doesn't mean it's not important. It's sort of pointing to like enormous gaps in the literature for great project topics. And so just in general, like this is an important but nascent field, which is generally like a great place to look to get into like a research field where you have the opportunity to make an impact. So welcome to the class. I'll see you guys on Thursday. Last lecture.
How's it going? I've been seeing like messages. So I have like published research. It's nice to be back.
Oh.
I refreshed the guitar. From there, mostly doing like rag stuff.
So he didn't have the agents, but he talked of the hypothetical.
Like in real
Yeah,
life.
yeah. I filmed out
Yeah.
we're going to
See, like, I think I have an idea.
rather than like related.
So like guarantee.
Where are your drivers? I like research still, so I try to.
For things. No, it's like I like kind of like, I mean, not like